Alright guys, thanks for coming today. Today our lesson is going to be about parallel and series circuits. To start with, we're going to do a quick review of Ohm's law for you guys, because I know that stuff can be a little bit tricky, so we're going to brush up on it before we move into the circuits. All of the parallel and series circuit stuff that we're going to talk about today is firmly rooted in Ohm's law and a couple of other kind of electricity fundamentals. So we'll start with the big one. So as you can see up here, Ohm's law is really just an evaluation of the relationship between current, resistance, and voltage. And here is the kind of colloquial chart that's used to express Ohm's law. So from left to right, we have the chart demonstrating voltage is equal to current times resistance. So in the last class, I know you guys didn't actually have the last class because today is our first day of class, but theoretically we would have just finished talking about current, resistance, voltage, power, all of those kind of fundamentals. So I'm just going to assume that we're all on the same page there. But the next middle slide, or chart, is showing current equal to voltage over the resistance, and then resistance is equal to voltage over current. So as you can see, it's really just a balancing act between the variables. Depending on what you need to figure out, what your unknown is, you can apply the known variables to this formula and quickly figure out what you don't know. The great part about Ohm's law is that it always works. So this can be, I find it as like a comforting, like safety blanket almost when I'm working through circuit problems, right? Mm-hmm. Ohm's law is never going to be wrong. So if what you did doesn't satisfy Ohm's law, then you have messed up, right? Mm-hmm. Okay. But if Ohm's law, is true, right? If your math works out and everything checks out, then it's kind of satisfying knowing that you've done everything correctly, right? So it can be a nice safety blanket there. So moving on from the voltage, current, and resistance relationship, we have a similar chart showcasing the relationship between power, current, and voltage. And I'm not going to beat it to death, but as you can see, a similar relationship is apparent between those three variables as before. The cool thing about this, sometimes people refer to this chart as Watt's law, but the combination of the two of these charts can give us pretty much any information that we need to know about a circuit or a part of a circuit based on any of these variables. So when we move on from this slide, I know a couple of you are taking notes, we will see kind of the combination of the two where you can sub out one variable for a set of variables to be able to find any permutation of information that you need to know. Okay. So if y'all are okay with me moving on here, yeah, I'll move forward. So this is the big chart that sometimes you'll see this expressed as like a big wheel with variables on the outside and all that kind of stuff. That one is a little bit confusing in my opinion. So this chart is something that I would prefer. It kind of spells out what you know and what you don't know and how to find it, right? So if we have current and resistance up there in the top right, we can figure out our voltage or we could figure out our power, right? So you move down the left side of the column, you say, what do I know and what am I looking for as you move to the right? So between these three handy charts, we've really got the roadmap for figuring out all we need to know in terms of voltage, current, power, resistance, all that good stuff. The stuff we're here to learn about today. All right. So, as I said at the top of the class, the whole thing is really about series and parallel circuits. If we have knowledge of Ohm's law, and its fundamentals, then we can start to dive deeper into the actual circuits themselves. So before we move on and kind of dive into what a series and parallel circuit is, I've got a little demo of a power amp. We've got 2 speakers. So I'm going to kind of ask you some hypothetical questions about the system that we've got here, and maybe your gut reaction to how you would expect it to behave, and then we'll measure it and see how it actually behaves. Okay. So the first thing that I've got right now is one speaker. It's just hooked up, right, by itself. So we're going to listen to it. A nice, wonderful 90 hertz. So we only have one speaker going currently. And what I'm going to do is actually switch over to this dot cam. I know it's a little grainy, but it's the best we've got to work with. So I'm going to measure the voltage being applied across that speaker. If my phone will cooperate. So right now we can see we have 2.6 volts dropped across the speaker. Okay. So, wonderful. I'm not going to touch the phone output. The phone output's going to stay the same. The gain on the power amp is going to stay the same. So the only variables that we're changing are adding speakers to the equation, if you will. So, as I add the second speaker, what do you guys expect to happen to the voltage? To drop.
Not sure.
I'll let you think about it while we...
Would it stay the same?
Could it stay the same?
That's kind of what my brain is thinking too, actually.
I'd like to think it stays the same, unless...
So, based on our handy little chart, okay, we established a relationship between voltage, current, and resistance. If we assume you guys have said the voltage is going to stay the same.
That's our guess, and then
That's your
Andy
guess?
guessed that it's going. You said increase, Andy?
Drop.
Or
You
drop?
think the voltage is going to drop? Well, let's look. Let's look what happens to the voltage.
Well, wouldn't it drop because you're trying to now split the load, per se, between the two?
That's a good question. So, what happened to the voltage on this speaker?
It's reduced by half, effectively.
Okay. So, intuitively, what could we say maybe about these 2 speakers? We know that the voltage just dropped in half.
Twice the resistance.
Twice the resistance. Okay. So, if we have twice the resistance, now, let's observe something else then. Our whole voltage, right? The same voltage that we just had applied before. So what's happening is we're indeed splitting the output voltage of the power amp has remained the same. The input voltage stayed constant. The gain stayed constant. So the output voltage was constant, right? So, but then we added another speaker in series. So we'll come to find out here in a second, and the voltage split across the 2.
Okay.
That's pretty cool. Well, there you go. That's why I'm here.
Right.
Okay.
All right, so that's kind of our first setup. Now let's look quickly at what might change if we were not using a series circuit, but instead a parallel circuit to hook these 2 guys up. So
Well, what's good?
what's the expected behavior that you all are postulating would happen with
Parallel?
a parallel circuit, right? We're assuming that it's different than series, or is it? Is it, you know?
I think the voltage would be, I think it'd be
The same
I hope
across
that
both
it
Now I'm
speakers.
thinking it this would
You
be
bet,
the same.
okay.
Yeah.
So we'll see. We'll see.
We're probably about to bat over too. It is, yeah.
So we have what?
It's actually a little more.
Yeah.
Looks
So
like it is, yeah.
I would take that slight variation with a grain of salt.
Just
We're
round
still
it
in
off.
within the kind of tolerance of the same circuit as before. Love if my phone didn't automatically shut off every 10 seconds. Same
Wow.
voltage
Okay.
across both speakers.
Mhm.
Okay. So, I remember this from when I took the signals and systems class. We just magically created energy, right? We hook something up in parallel. We can do this as many times as we want and have voltage everywhere, correct?
Mhm.
What's the trade-off, right? We saw Ohm's law before as the relationship between some variables, right?
Mm-hmm.
So we're saying the voltage has done what? Stayed the same across all of them. Now something that we didn't do just a second ago, we can do for this is measure the resistance or impedance across the circuit. So right now we're showing 3 ohms, okay?
Mm-hmm.
If we measure just one of these guys, we have double that, correct?
Mm-hmm.
As we can see on the dot cam. So with one speaker, we have 6 ohms of resistance. With 2 speakers hooked up in parallel, we have 3.
Mm-hmm.
Okay, so what happened to the resistance? It went down,
Yeah.
correct?
Yeah.
Right. And the voltage did what? Stayed the same.
Mhm.
Okay, so if the voltage stayed the same and this went down, what happens to the current? It goes up, right?
Yeah.
Remember this balancing act
Mhm.
before? Okay, so now we've kind of puzzled out or teased out the fundamental problem with thinking that we can just take parallel circuits,
Yeah.
right, and just continue to split them into infinity, right? As we can see, the more things we put in parallel, the resistance actually goes down. Kind of counterintuitive, right?
Mhm.
We have more speakers.
Hmm.
And if we looked before, you also intuited that when we added the 2 speakers in series, the resistance went up, right? We observed a drop in voltage across each speaker. So the interesting dynamic here is, depending on how we connect our speakers, series, parallel, or just one speaker by itself, we're observing a couple of things changing. The current and the resistance, and in fact the voltage dropped across each speaker. So the balancing act that you saw in the equation is indeed borne out in real life, and that is something that we as audio engineers have to pay a lot of attention to when we're setting up speaker systems. Something we'll get to a little bit later. All right, now that we've had the fun with the toys, right, the speakers and the power amps and the stuff that we like, we're gonna move on to a little bit of a PowerPoint demonstrating some of the stuff that we intuited. We're gonna kind of put words to it. So, a series circuit this is kind of the very heady, you're getting this definition because we're in college, right? A series circuit can be defined as a grouping of lumped elements such as resistors, or speakers in our case, that are connected along a single conductive path such that current flows in one direction through each element, or from element to element. So earlier when I had a series circuit set up, current left the power amp, traveled through one speaker, into the next speaker, back to the power amp. We had one single conductive path from element to element. The second part of this, the voltage of the circuit is dropped across successive components, but current is maintained throughout the entire circuit, and that's dictated by the relationship between the total resistivity of the circuit and the total voltage applied, right? So that's just Ohm's law kind of broken out into a paragraph, right?
Okay.
But we also saw that in real life when we measured it. Right? We started with an output voltage of around 2.6 volts from the power amp. We saw that dropped across one speaker when it was the only element. In fact, that was in itself a series circuit, right? We had the power amp and we had one speaker. We had 2.6 volts dropped across the whole speaker. Now, we added a second speaker in series. We saw the voltage of the circuit was dropped across the successive components, correct? We had half of it on the first speaker, half of it on the second speaker, and when we measured across both, we saw our total output voltage.
Yeah.
Yeah.
So, you know, the science works out. Now, this is a graphical depiction or a circuit diagram of a series circuit. What you're seeing there is the voltage source indicated by the positive and negative right here, and 3 resistors hooked up in series. Fairly simple circuit, you know, just 3 resistors and a voltage source, but that is how it would be depicted in a circuit diagram, and in fact we're going to use something similar to that here in a second to kind of compute and think about the math behind series circuits. So you can sketch it out now, but we're going to return to it here in a second,
Cool.
so don't stress too much. All right, so the next part of this is again, we measured this, we put words to it, but this is how maybe mathematically or formulaically we would express this. Voltage in a series circuit. The total voltage of the series circuit is equal to the sum of the voltages dropped across each element. So again, earlier, 1.3 volts, 1.3 volts, together we had 2.6 volts. So we had the total voltage. The total current in a series circuit is the same at all points of the circuit. That can initially seem kind of confusing, I think. Current in that the series circuit versus the parallel circuit is a little bit of a sticking point. But if you think about it, we have a total resistance of the circuit, correct? We have a resistance of each speaker, they add together. That really forms what can be described as a single lumped element. You simplify the circuit. So if we think of those 2 speakers as one, right, we have one 6 ohm speaker here and one 6 ohm speaker here. And this resistance, you know, the next part, we see that we add them together. If we add them together, we have 12 ohms of resistance, correct? So we have the voltage total and we have 12 ohms of resistance, and we find our total current. The current only has one path to flow. So the total amount of current leaving the power amp has to come back. Okay, so
Okay.
we can't lose any, we can't gain any with this simple series circuit.
Stays
So
consistent.
stays consistent throughout the whole thing. You could think of it as really just one path, and the current flows through there. In this diagram before, it's indicated with arrows there. All right, so now comes the fun part of, we're going to actually draw a circuit up here, and then we're going to work through it, or rather, you all will work through it. And
Phillip?
yeah, Andy.
Is there, like in that circuit diagram you showed, does voltage and current, do they travel in opposite directions?
So voltage doesn't travel. Voltage is not something that moves. Okay,
Got it.
it's definitely a big misconception about electricity and electronics in general. Something that we would have covered in the past class, but I don't mind going over it briefly. It's really the potential difference between 2 points in a circuit. Okay, and if you want to think about it in brief, the potential difference is just the ability to move current from one point to the other. Okay, so this is there is no flow of voltage per se.
Got it.
All right, so this is going to be R1, this will be R2, and this will be R3. And all of the numbers that we're going to use today really are firmly grounded in audio numbers, audio fundamentals, if you will. Speakers, 8 ohms, 16 ohms, 4 ohms, in that ballpark. So we're going to try and keep this applicable, all right?
Okay.
So the total voltage given by this voltage source, this could be a power amp, could be a battery, it doesn't really matter. It is applying voltage to the circuit. Okay, so we have 2 volts total across this. So now, we still have that up here. So I'm gonna ask you a couple of questions. You guys have the little Socrative thing ready to go, or if you don't, if you don't mind pulling it up.
Yeah.
Yeah, sorry.
Yeah. So the first question, or kind of information that I want about this circuit is for you all to find the total current through the circuit. Okay. So in order to do this, I'm going to give you some help, right? This is the first time we looked at parallel and series circuits. We've already said that in the slide before this one, the total voltage is dropped across the entire circuit.
Mm-hmm.
And then the total current is a relationship between the total voltage and the total what?
Resistance.
Correct. So the resistance of all of these elements, we would call that RT. This is VT, voltage total, right? So the total resistance of the circuit is going to help us find the total current. So if we have RT as our unknown up there, we kind of have a handy cheat sheet. How are we going to go about finding the total resistance for this circuit?
There's a 1 plus 2 plus 3, so the total of ohms in the, so 32. Yeah.
So 8 ohms plus 8 ohms plus 16 ohms, correct?
Okay.
Right. So you exactly. R1 plus R2 plus R3 gives us the total resistance for the circuit, and that is, in fact, 32 ohms.
Okay.
So now that we have that handy piece of information, where do we go from there? The question that you should see on your little Socrative quiz thing right now, it's asking for what? The total current, right?
Mm-hmm.
So IT equals question mark. A very bad one. There we go. Question mark. So IT up there, we see that it says equal to I1, I2, I3, right?
Mm-hmm.
So we kind of need some other information to solve the problem. But hopefully you all remember from earlier on, we've got a handy formula or relationship between resistance and voltage to give us the current.
Mm-hmm.
So what would that be?
Voltage divided by resistance.
Voltage. So you're saying current is equal to voltage divided by resistance. And where did that come from, Dustin?
From ohms.
Ohm's law, right? Yeah, exactly. Okay, so now that we have this, we have our total resistance, and we have our voltage total, correct? Where's the voltage total coming from?
Voltage total equals 2 volts.
Correct. I gave you that. Yeah,
Mhm.
that's the voltage source here. So, let's see. 2 volts over 32 ohms. That's going to give us our current total. So, if you want to put your answer in on your little soccer hit thing,
I need to divide it.
And so, current is measured in milliamps.
current measured in amps in this instance, you will find out that the answer is in milliamps.
Okay.
Could be amps, 1 amp total, right?
In audio, are we mainly working with milliamps?
It,
Is that what you
it
typically
depends on the circuit. So in small signal circuitry, like when we're talking about the inner workings of a preamp and EQ, something like that, the current is small, milliamp range.
Mhm.
Okay, but when we're talking about something like power amps and speakers, we'll find out that the current draw can actually be pretty high.
Really?
Yeah.
Like in actual amps?
Yes, yeah,
Wow,
in the
that's
amps, tens of amps. So
Okay.
yeah,
That's pretty high.
it'll be curious to see when you guys do your Nolansville show how much current you guys draw for your line array and all of that stuff.
Yeah.
So did we all answer here? I think I'm missing one, but I don't know if that. You're yeah, okay. That's all right. Oh look, everyone got 100%. That's great. So we should have advanced to the next slide on your soccer div. That work for you? Okay,
Yes.
cool. So I'm not going to give you any help on this one, but if you could answer that question about the circuit that you're seeing, then we'll kind of talk about the results.
So if we get this answer wrong, it's not going to get you in trouble or anything with
Oh
your
no,
teaching?
no.
Okay, I just making
Right
sure.
or wrong, we can talk about the
I
results.
just wanna
That's
make
the
sure.
whole point of this.
Don't want to mess you over.
That's okay. Hope, yeah.
Let's think here.
Alright, I'm doing it.
No pressure. So,
No voltage.
did you answer, Ben?
Is that a quick question? I can't, do you want me to? Oh,
Yeah, just
Okay, I'm doing it. Going in, boys.
I just realized I thought of it backwards.
I'm-
Now.
all right.
You're welcome, or I'm very sorry, Phillip.
That's all right. That's all right. Just an answer was needed. So we had 2 out of the 3 of you select false, and then someone said true. That's okay. So if you said true, that was actually the incorrect answer,
Yeah.
which is all right. The question was the current through resistor 3 is less than the current through resistor 1. Now, if we look at the mathematical relationship of this series circuit, why is that not true? Peter, can you help me out?
It's, well, the current only flows in one direction, right? And so the current's the same through all of them, right?
So,
Say it one more time. I want to hear. Can you
Well,
say that
there's
again? I
only
just wanna
one
hear that again.
current flow, because you can see there's only one stream
Mm-hmm.
through the whole component. So the current would be the same through all of them.
Oh.
The,
Yeah.
the voltage would change through each one.
so if we look at our current flow in this kind of translucent green kind of thing, current flow will be indicated differently depending on the diagram. You have conventional and electron current flow. It's either going to flow negative to positive or positive to negative depending on what you look at. It doesn't really matter. So the electrons flowing from negative to positive, as Peter mentioned, we only have one path for them.
Mm-hmm.
So if we have the total current throughout the whole series circuit, stays the same consistently. it is in fact going to be the same, entering this lumped element, resistor 3, same at resistor 2, resistor 1. We're not losing any current as it passes through, okay?
Okay.
So that might be a slight misconception about how current works. We're not losing it here,
Mm-hmm.
okay?
Okay.
So, yeah, Ben.
I mean, I'm just in my head. It would make sense then. You have why resistance ends up going down. In order for that to work, it's so the current can. And please correct me if I'm wrong, but I'm just thinking on a pragmatic level here.
Okay,
That it's
yeah.
like resistance goes down. It's like trying to get through a river. It's like
Yeah.
You have
The
less
less
resistance if
resistance,
you're gonna be
the
going-
more current flow,
Yeah.
right? Okay. So,
dumb analogy. You're welcome.
no,
There you
that's, if you can conceptualize it using your own, analogy,
Yeah.
that's perfect. A lot of people do choose to use the water analogy with electronics and electricity. So
Which is ironic that water is the one thing that kills electronic circuitry.
there is that.
Oh, yeah.
All right. So the last problem it's on your soccer, Dave. It's a little bit of a short answer, and it's asking what's the voltage dropped across each resistor, right? So in order to figure that out, we need to know pieces of information about each element, right? I'm looking for the voltage dropped here. Man, having working markers is essential to this. We'll just use black. So the voltage dropped across this is V1. The voltage dropped across this is V2, and similarly V3. Alright, so we have Ohm's law to help us, right? Voltage is equal to what?
It's equal to current times resistance.
Voltage is equal to current times resistance. So, we have found out a couple of pieces of information that will help us here. In that last Socrative question, we figured out what about the current through the circuit,
That was 62.5 milliamps.
correct? And it stayed constant throughout, right?
Mhm.
Right. So if we have 62 milliamps of current through this lumped element resistor 3, how do we find the voltage?
Would it be 62.5 times 16?
62.5 milliamps
Milliamps
times
times
16.
16.
Right. Yes. So that is indeed how you would figure it out.
Okay.
So if you want to do that for each resistor,
Sure.
Okay. Or do we need to do it by, like 0.00625 to be,
0.06.
so yeah, 0 points, yeah, do we need to do it by that instead?
correct.
Okay.
If you were being really technical and like making notes to yourself while you're creating a circuit or something, would you express volts as like amps over ohms, like, or just as its own like unit? Like I'm thinking about like I had a physics problem in high school where like we were trying to express mass as like including every other like metric that exists except mass and figuring out a way to
Yeah,
figure
I see what you're saying.
Is that like the same kind of thing?
You could certainly choose to do that. You could think about the current through that element, and you would have the voltage dropped across it. So, yeah, I mean, what you're essentially asking is, can I represent a variable in Ohm's law with a combination of other variables?
Yeah.
Right? Yeah, totally. And in fact, that is a big part of that chart that we looked at earlier.
Mhm.
That's how that chart was created, substituting two variables for one and kind of deriving an additional equation from
Cool.
that. So,
Cool.
Interesting. And then, yeah,
so what did we get here?
2. Oh,
Two?
here for specifically for 3, 1.
1 volt,
Yeah, 1 volt.
and then voltage across 2,
0.5,
0.5 volts.
and then 0.5 for, yeah.
Uh-huh.
And if we add all of those together, what do we get?
All the
2
volts.
2 volts.
2 volts.
You remember when I said Ohm's law and this stuff? It's like a comforting, like, safety blanket, right? We just solved all of the math, and it all worked. we got back to 2 volts. Our resistances all make sense. Everything is great, and the universe is happy. So, yeah, this is kind of the first step for you guys into circuits. I like to start with a series circuit first. It's kind of a little bit more intuitive. Did it all
Yeah.
kind of blow your mind a
light
little bit?
bulb. Yeah, man, that's
In the
great.
answer, do you want us to list the total
Uh,
voltage as well?
Uh,
Or just the current drop
you can
for
just
all the resistors?
yeah, across each
I put like
resistor.
resistor 3, 1 volt, which is that's
Yeah.
Okay.
I-
Is
I
it okay
had
if I
seen-
put V1 or V2?
It doesn't have
It's
to be
same,
super
same
specific.
difference.
So,
Okay.
regarding the positive and negative of the voltage
Mhm.
source, I see that
There you
current flows from negative to positive.
Correct.
Is that because of like magnets, the way that they resist, like putting 2 of the same negative like magnet together, they repel, and electrons are negatively charged. So they want to go to positive. Is that how that works? I don't know if I'm saying that clearly. I'm just wondering why. My
Yeah,
intuitive
so-
thought was
So earlier when I said conventional electron flow versus electron
Mhm.
flow, right? So in some textbooks you get electrons flowing from positive to negative in a voltage source, and then in others you get negative to positive. Negative to positive is how the electrons actually flow.
interesting.
So
Got it.
that would be the
Interesting.
I don't know if
Kind
that
of
helps.
intuitive.
All right, so now let's move on to parallel circuits. We gotta move a little bit. So a parallel circuit can be defined as a grouping of lumped elements such as resistors that are connected with multiple conductive paths, allowing current to split and flow through multiple branches before returning to the source. So earlier when we had the speakers hooked up in parallel, you may have noticed that we had one set of wires running from the power amp to the first speaker, and then an individual set of wires running from the first speaker to the second speaker. We had a lot more wire involved. It's still set up here, right? We have a lot more wire involved here than the 3 individual wires that we saw with the series circuit. So we're adding multiple paths for current to split and flow. We have multiple branches. So the parallel circuit is, clearly different in its function than the series circuit.
Mhm.
And as we saw earlier, the voltage applied to a parallel branch of a circuit is dropped across all of the elements equally. Okay, so the output voltage was dropped across the parallel branch of the circuit, which is the 2 speakers hooked up in parallel. The voltage was applied equally. Depending on the resistance of each branch, the current will split proportionally.
Okay.
So we have this parallel circuit here. So if we look at that, we have the same voltage source and the same resistors. We'll do a problem using this kind of setup with the exact same values we just used and see what changes about the 2. But we have multiple branches in this circuit for current to flow through. Okay, inherently that's going to change the circuit. Again, I'm going to skip ahead a little bit. You'll be able to finish up your drawing when I draw it up there.
Okay.
But we're going to move on to the mathematical stuff. Okay, so again, the total voltage dropped across each element of a parallel circuit is the same in our case earlier. Again, the output of voltage of the power amp dropped across each element in parallel. The total current of the parallel circuit is equal to the sum of the currents through each individual branch of the circuit. So now you can think of the current functioning similarly to the voltage in the series circuit, right? The current through each element is actually going to sum together and result in the total current for the circuit. Now, the last part, the resistance, this is the part that it's really fun to say because it sounds very scientific and, it's great. The total resistance of a parallel circuit is equal to the reciprocal of the sum of the reciprocal resistances of each individual element. Yeah, that's a little bit much. Okay, so as you can see there, though, you take the reciprocal of each individual element, we sum those together, and then we compare that to the reciprocal of the total. You'll see how that works out when we actually do it. Once you do it, you know, with a calculator and you kind of work it out, it kind of makes a little bit more sense for that. All right, let's. Oh, that's already frozen there. Okay, so now we're gonna draw the same kind of circuit as before, in that the voltage source is the same. Now what changes is our arrangement of resistors. Alright, let's do arm. Okay, so this is all good. Let's hop on over to Socrative and see what I'm asking you. So do you guys have that displayed on your screens up there? The total resistance for the circuit as shown on the board. So, the total resistance, how do we find that out? Well, we figure out what the reciprocal of the sum of the reciprocal resistances of each element is, right? Again, fun to say. So, if we have these,
1/8 plus 1/8 plus 1/16.
and that's equal to 1 over RT. Okay, so if you all want to find out the that for me and put it into Socrative, that'd be wonderful. So, Dustin, the loud makes me think you're puzzled.
Well, I'm just trying to keep up.
Yeah, no worries.
So-
So this, maybe the simpler way to think about this is to do this part of it, figure out all of this stuff.
Yeah.
Okay, once you have that,
I guess
take
what-
that number.
I think what I'm trying to think is like, do I need to do it as far as like 1/8 plus 1/8 plus 2/8? Like, do I need to change the fraction to then match things up?
Yeah, you can absolutely do
Okay.
that.
Math is never
You
my
can
strong
also
That's
suit,
fair.
so that's
No
why
worries.
I'm-
You can also
Okay.
just convert them all into decimals and then add the decimals together.
Yeah.
However
Okay.
it's. So, but the big thing is simplify this part of it. Right?
Yeah.
Take the reciprocals of each individual part, figure out what that answer is, and then just take the reciprocal of that. Okay.
This resistance.
So if we just add all those numbers together as they, say we converted them to decimals and added them,
Mhm.
that's what 1 over RT is.
Correct. So if
So
you
then-
want to find RT,
Oh,
The
wait.
one divided by that number?
Correct.
hold on.
so I'm going to help you all out a little bit. If we take the reciprocal of 8, we get, and I'm going to use decimals because that'll make your life easy, 0.125. We have two of those, right? We have 1/8 and 1/8, so 0.125 plus 0.125, correct?
Mhm.
So if we take 16 and get the reciprocal of it, it should be, what? 1/2 of this, right?
Mhm.
It's not,
Oh,
yeah, so 1/2 of that is 0.0625. So, adding all of that stuff together, we get, what do we get?
I got 3.2.
What about
Oh,
this
sorry.
one? Yep.
Uh,
0.3.
Yeah, so 0.3125. So you all see where we got that from. Yeah, so once we have that, then it's actually fairly simple. You just take the reciprocal of this number. So 1 over that is going to give us your answer. And whenever you have it, you can just put it into the little thing,
Okay.
and I'll check up on you all.
Okay.
Okay.
That's really interesting.
Yeah.
Hmm.
Mark out that part of my initial math.
Yeah.
So we all got 3.2 ohms, right?
Yeah.
Does that blow your mind a little bit? Like what? We have resistances. We're putting more of them together. How
Yeah.
did we get less? Well, we've added more paths for current to flow through.
Mm-hmm.
We've dropped the resistance. Okay. So the day before this in my theoretical class, right? You guys are unfortunately getting day 2 of this, but I like this a little bit better. That we would have talked about resistance and like the cross-sectional area of resistance to current flowing. So if we add more area, we have more path for current to flow. Okay. So the total resistance, in fact, does go down. That's cool. So let's say that before we even go on and do any more math, we figured that out earlier with the speakers. But if we have, what's Ohm's law again? Voltage equals?
Isn't it I times
Current
R?
times resistance.
Yeah.
Current times resistance, right? We're saying that V stayed the same,
Mm-hmm.
the voltage source, as the last problem that we just did.
Mm-hmm.
What happened to the resistance?
It went down.
Last time we had how much resistance for the series circuit in total? 8 plus 8 plus 16? 32.
Okay.
So we had 32, now we have 3.2.
Mm-hmm.
So the resistances went down
Mm-hmm.
by a factor of what? 10. Now, what would you expect for the current to do?
To go up.
By
Factor of 10.
a factor of 10.
Okay.
What was the current of this last circuit? The total current.
62.5 milliamps.
Yeah.
62. If we went up by 10 times, would the total current for the parallel circuit be higher or lower than the series circuit? Higher, right? Yeah.
Okay.
So we're going to skip that question. But we've just deduced that the total current goes up, in fact. Okay? We could have measured that with this ammeter. It's a little funky. It isn't always the greatest, so I chose not to do that. But we would have seen that when we put these in parallel, our current goes up. Our voltage stayed the same, our current goes up. We don't really talk about power much, but if we looked back at the first slide, or the second slide where we were looking at Watt's law, right, power is equal to current times voltage. If the voltage stayed the same and the current went up, then the power went up.
Mm-hmm.
Paralleling these speakers or resistors allowed us to increase the power. The cost is increased current draw, okay? This power amp is a real physical item
Mm-hmm.
that has limits because of physics,
Mhm.
okay? So there's only so much current that we can ask from the power amp.
Mm-hmm.
But the way that we've arranged this circuit, we're drawing more current, we're getting more power. So there's some potential upsides to that, okay? So
But we can only do it like so much before we.
right. So this power amp will tell you, it's expressed, it's a power amp, right? So 200 watt power amp. It's telling you this is the amount of power I have to give you. Based on your output voltage and the resistances that you hook up to it, you can figure out what the max current draw is, right?
Hmm.
So we don't really have enough time to go through the current through each branch, unfortunately, because we're kind of bumping up on time. But shortly explain it, up there, the total current through the parallel circuit is equal to the sum of the currents through each individual branch.
Mhm.
Okay? So if we have 625 milliamps through the whole circuit here, we have to have 625 come back. And just now I'm drawing the current flow completely opposite to the way that I just did last time. See? We're all good. It's just polarity. Okay, so at this juncture here, this node and this node, current is going to split here and here,
Mhm.
and then here and here. And the way that it splits is based on the resistances. So we know that there's 2 volts across each lumped element. We know their individual resistances.
Mhm.
Based on that and Ohm's law, we could figure out the current through the circuit, right? We did it earlier. I equals what?
V over R.
V over R, right? So I equals V over R. You'd simply go through for each element in the circuit and grab all of those individually. Again, unfortunately, we don't have enough time to go over that because 50 minutes is short
Yeah.
compared to an hour and a half. But let's move on and just think about something in brief. The series parallel circuit. We didn't talk, or we didn't draw one of these. We didn't do this. But as you can see there, it's just a circuit that contains series elements and parallel elements, right? And I put a little paragraph there explaining how we would solve it. We're not going to go through this, but we have a series element and we have 2 parallel elements. If we simplify the 2 parallel elements, R2 and R3, and we represent them diagrammatically, like conceptually, as one element, the parallel resistances of R2 and R3, you see there, I'm saying, representing it with the equivalent lumped element of R2 in parallel with R3. That's just saying this is now a super resistor of the 2, okay? That big resistor, smaller actually, as we know, because of the parallel relationship, would then be in series with the first element. We could figure out the total resistance, we could figure out the total current. So, series parallel, we're just combining them.
Cool.
So, how does this manifest in reality? How does it apply to us? On the left there, we have a guitar cab, and that is wired up in a combination of series and parallel to provide the right load to the amplifier. Again, we said that the amplifier can only provide us with so much current, right?
Mhm.
So we need to arrange those speakers in a way that satisfies the amplifier. We don't want to lower the resistance so much that the amplifier provides too much current, right? That will damage, the amplifier. You don't want that, okay? The second part of that, on the right, as I said earlier, you guys are flying a PA at your Nolansville show. It's going to look a lot like that, the line array. It's the classic, the staple of all live sound reinforcement these days. Well, how do you get all of those speakers, their power?
Yeah.
It's a combination of series and parallel circuits. You may hook them all up in parallel, depending on your power amp, or you may say, well, I need this guy in series with these 2, and then that whole combination's in series with this, or in parallel with this, to provide the right load on the power amp. Okay? So that leads us to our last little bit here, which is our kind of hypothetical scenario that I want you guys to think about and to come up with a solution for the next time, and we'll talk about it at the start of next class. Our hypothetical scenario, we have 2 power amps and 3 speakers, that should say 6, 3 speakers per side. So ideally, 1 power amp, 3 speakers, 1 power amp, 3 speakers.
Okay.
So we have stereo.
Okay.
We like stereo. Okay. So each power amp has a fixed output of 15 volts and a maximum current output of 1 amp. 15 watt power amp. That's a very small power amp, but that's fine. We have two 16 ohm speakers and one 8 ohm speaker per side. You have to figure out, how do I connect these in order to create a system that takes maximum advantage of the power amplifier without exceeding its spec. Okay? So we can run the power amp at 15 volts and then provide a certain amount of current. If you exceed that, you have a problem, right? The power amp is going to burn up. So your task is to create a hypothetical system that would satisfy these constraints. 1 power amp per side, 3 speakers on each side, and I've kind of given you a hint, 2 16 ohm speakers and 1 8 ohm per side. Cool? It won't be a series circuit. It won't just be a parallel circuit. Some combination of the two would be required to solve this. Okay? So I'm going to leave you guys with that, and if you could work on it for next time, that'd be wonderful.
Yeah.
All right, you guys have any questions?
Not yet.
No? Cool. All right, thanks. I guess class is dismissed.